Download this code from codegive.com, link in the description below. Advanced Tuning and Operation Guide for Block Storage with Ceph. This comprehensive guide delves into advanced tuning and operational aspects of Ceph block storage, RBD, providing in-depth explanations, practical code examples, and best practices for optimizing performance, reliability, and scalability. We'll cover key configuration parameters, monitoring techniques, and troubleshooting tips to help you effectively manage your Ceph RBD clusters. Table of Contents *. 1. Understanding Ceph block storage, RBD. *RBD Architecture Overview. *RBD Features and Use Cases. 2. Hardware Considerations for RBD Performance. Storage Media, SSD versus HDD. Network Infrastructure, Bandwidth, Latency. CPU and Memory Requirements. 3. Ceph Configuration and Pool Optimization. Crush Map Design and Placement Groups, PGS. Pool Parameters, PG_number, PGP_number, Size, min_size. Object Size and Alignment. Tiering and Caching, using Cache Tier. 4. RBD Client Configuration and Tuning. Kernel RBD, KRBD, versus QEMU RBD. RBD_cache and RBD_read ahead parameters. IO scheduling, deadline, NUP, MQ. Multipathing and connection optimization. 5. Performance monitoring and analysis. Using Ceph S, Ceph OSDF, Ceph PG dump. Rados bench for benchmarking. Grafana and Prometheus integration. OSD profiling with perf and flame graphs. 6. Advanced RBD features and techniques. RBD snapshots and cloning. RBD mirroring, disaster recovery. RBD encryption. Quality of service, QoS, using Ceph OSD priority. 7. Troubleshooting common RBD issues. OSD down/out issues. Slow request errors, slow operations. Performance bottlenecks. 8. Best practices for Ceph RBD management. Regular monitoring and alerting. Capacity planning. Software and hardware updates. Security hardening. 1. Understanding Ceph block storage, RBD. RBD architecture overview. Ceph RBD presents block devices to client applications through a distributed object storage system. Key components. Ceph OSDs, object storage daemons store data as objects. Data is replicated across multiple OSDs for redundancy. Ceph monitors, MONs maintain cluster state information, including the crush map. Ceph Rados, reliable autonomic distributed objects store the underlying object storage layer. RBD, Rados block device the layer that provides block storage functionality on top of Rados. RBD images are striped across multiple Rados objects. Crush, controlled replication under scalable hashing, an algorithm that determines data placement based on cluster topology and failure domains. RBD features and use cases. Scalability. RBD can scale to petabytes or even exabytes of storage. Reliability. Data is replicated across multiple OSDs, providing high availability and data durability. Snapshotting. Create point-in-time copies of RBD images. Cloning. Create new RBD images from snapshots. Copy on write ensures space efficiency. Thin provisioning allocate storage space only as needed. Consistency supports consistent snapshots. Integration integrates well with various virtualization platforms, example KVM, Xen, VMware, and cloud orchestration tools, example OpenStack, Kubernetes. Common use cases include virtual machine storage, disk images, database storage, general purpose block storage. 2. Hardware considerations for RBD performance. Storage media, SSD versus HDD. SSDs offer significantly lower latency and higher IOPS compared to HDDs, ideal for workloads that require high random I/O, such as databases and virtual machines. HDDs cost-effective for large capacity storage, suitable for workloads with primarily sequential I/O. Recommendation: use SSDs for OSD journals/write-ahead logs, WALs, and for high-performance OSDs. HDDs are suitable for cold storage or archival workloads. Consider using NVMe SSDs for even higher performance. Network infrastructure, bandwidth, latency. Network bandwidth. Sufficient network bandwidth is crucial for data transfer between OSDs and clients. 10 GBE or faster networks are recommended for production environments. Consider using link aggregation, bonding, for increased bandwidth and redundancy. Network latency. Low network latency is essential for optimal performance. Use a low latency network fabric, such as InfiniBand or ROS, for demanding workloads. Network topology. A well-designed network topology can minimize the number of hops between OSDs and clients. Consider using a class network or spine-leaf architecture. CPU and memory requirements. CPU OSDs perform checksum calculations, data encoding/decoding, and other CPU-intensive tasks. Sufficient CPU cores are needed to handle the workload. The number of cores per OSD depends on the workload, the number of OSDs per server, and the number of client connections. Memory. OSDs use memory for buffering data, caching metadata, and performing other operations. Sufficient memory is needed to avoid memory pressure and performance degradation. The amount of memory per OSD depends on the workload and the number of OSDs per server. 16 GB or more of RAM per OSD is typically recommended. 3. Ceph configuration and pool optimization. Crush map design and placement groups, PGS. The crush map defines the cluster topology and how data is distributed across OSDs. Careful design of the crush map is essential for optimal performance, fault tolerance, and data locality. Crush hierarchy. Defines the hierarchy of failure domains, example rack, row, data center. Data replicas are placed in different failure domains to ensure data availability in case of failures. Crush rules. Define how data is distributed within each failure domain. You can create multiple crush rules for different pools and workloads. Placement groups, PGS. A logical grouping of objects within a pool. The number of PGS determines the granularity of data distribution. A higher number of PGS generally leads to better data distribution and performance, but also increases the load on the monitors. Example crush hierarchy. Calculating the optimal number of PGS*. A common rule of thumb is to aim for roughly 100 PGS per OSD. You can use the following formula. Total PGS equals, total OSDs *100, / replication factor. Example asterisk. If you have 10 OSDs and a replication factor of 3, you would need 10 asterisk 100 slash 3 equals 333.33. Round up to the nearest power of 2, 512 PGS. Setting PG underscore number and PGP underscore number asterisk. Asterisk PG underscore number, the actual number of PGS for the pool. This should be set before storing data in the pool. Once data is stored, changing PG underscore number requires data migration. Asterisk PGP underscore number, the number of PGS used for placement calculations. This can be changed after setting PG underscore number and can be used to trigger data rebalancing if the number of OSDs changes. PGP underscore number should ideally equal PG underscore number. Creating a pool with RBD asterisk. Asterisk pool parameters, size, min underscore size. Asterisk size, the number of copies of each object that are stored. For example, a size of 3 means that each object is replicated 3 times, replication factor of 3. Asterisk min underscore size, the minimum number of copies that must be available for write operations to succeed. For example, a min underscore size of 2 with a size of 3 means that write operations can proceed even if one OSD is down. Recommendation asterisk set size to 3 and min underscore size to 2 for production environments. This provides good data durability and availability. For erasure coding pools, these parameters have different meanings. Consult the Ceph documentation for details. Setting pool parameters asterisk. Asterisk object size and alignment asterisk. Asterisk object size asterisk the size of the objects that are stored in the pool. The default object size is 4 megabytes. Increasing the object size can improve performance for large sequential I/O, but can also increase latency for small random I/O. Experiment to find the optimal object size for your workload. While you technically can change it, doing so is generally not recommended after you've started putting data in the pool. Asterisk object alignment asterisk ensure that the size of your RBD images is aligned with the object size. This can prevent read-modify-write operations, which can degrade performance. Asterisk tiering and caching, using cache tier. Ceph supports tiering, which allows you to move data between different tiers of storage based on access frequency. A common use case is to use a faster tier, example SSDs, as a cache tier for a slower tier, example HDDs. Example, creating a cache tier asterisk. 1. Create a cache pool, SSD based. 2. Create a storage pool, HDD based. 3. Set the cache tier parameters asterisk. Asterisk cache mode. Asterisk write back, writes are written to the cache tier first, and then asynchronously flush to the storage tier. Provides better write performance but can lead to data loss in case of a cache failure. Asterisk proxy, writes are written to both the cache and storage tiers simultaneously. Provides better data durability but slower write performance. Asterisk hit underscore set underscore asterisk, configure the hit set parameters to track which objects are frequently accessed. 4. RBD client configuration and tuning. Asterisk kernel RBD, KRBD, versus QEMU RBD asterisk. Asterisk kernel RBD, KRBD, a kernel module that allows you to map RBD images directly to the operating system as block devices. Provides the best performance. Suitable for bare metal servers or virtual machines where the OS can be modified. Asterisk QEMU RBD asterisk allows you to access RBD images directly from QEMU/KVM virtual machines. Does not require any kernel modifications on the guest OS. Slightly lower performance compared to KRBD due to the overhead of QEMU. Asterisk RBD underscore cache and RBD underscore read ahead parameters asterisk. Asterisk RBD underscore cache asterisk enables the RBD client-side cache. This cache stores recently accessed data in memory, which can improve read performance. Enabled by default in modern kernels. Asterisk RBD underscore cache underscore size of cache in bytes. Asterisk RBD underscore cache underscore max underscore dirty, percentage of the cache that can be dirty, unwritten, before write-back starts. Asterisk RBD underscore cache underscore max underscore dirty underscore age, time in seconds before dirty data is flushed to Ceph. Asterisk RBD underscore cache underscore target underscore dirty, percentage of the cache the system tries to maintain as dirty. Asterisk RBD underscore read ahead asterisk specifies the amount of data that is read ahead into the cache when a read request is received. Can improve performance for sequential reads. Tuning RBD underscore cache and RBD underscore read ahead asterisk. You can adjust these parameters in the Ceph configuration file, ceph.conf, or by setting environment variables when mapping the RBD image. Example ceph.conf settings asterisk. Example using environment variables with RBD map asterisk. Asterisk IO scheduling, deadline, NUP, MQ. The IO scheduler determines the order in which IO requests are processed by the kernel. Different IO schedulers have different characteristics and are suitable for different workloads. Asterisk deadline asterisk attempts to minimize latency by prioritizing requests that are close to their deadline. Good for general purpose workloads. Asterisk NUP asterisk a simple FIFO scheduler that performs minimal processing. Suitable for storage devices with their own sophisticated IO scheduling, such as SSDs. Asterisk MQ, multi-queue block IO queuing mechanism utilizes multiple hardware queues to improve concurrency. Particularly effective with NVMe SSDs. Recommendation asterisk for SSD-backed RBD images, use the NUP or an MQ-based scheduler, example Kyber, BFQ, to offload IO scheduling to the device. For HDD-backed RBD images, the deadline scheduler can be a good choice. Setting the IO scheduler asterisk. You can set the IO scheduler for an RBD device using the echo command. Important asterisk replace RBD0 with the actual name of your RBD device. This setting is not persistent across reboots. You can make it persistent by adding a rule to /etc/udev/rules.d/. Asterisk multipathing and connection optimization asterisk. Asterisk multipathing asterisk allows you to access RBD images through multiple network paths, improving availability and bandwidth. Use DM multipath for this purpose. Configure your system to automatically fail over to another path if one path fails. Asterisk connection optimization asterisk. Asterisk increase the number of concurrent connections to the Ceph cluster. This can improve performance for workloads with high concurrency. This is especially applicable in virtualized environments. Asterisk tune the TCP parameters to optimize network performance. 5. Performance monitoring and analysis. Asterisk using Ceph S, Ceph OSDF, Ceph PG dump asterisk. Asterisk Ceph S, Ceph status provides a high-level overview of the cluster status, including the health status, usage statistics, and OSD status. Asterisk Ceph OSDF, Ceph OSD disk-free displays the disk usage for each OSD. Asterisk Ceph PG dump, Ceph placement group dump provides detailed information about the placement groups, including their state, object counts, and statistics. This output is extensive, but useful for deep dives. Consider piping to tools like JQ to filter the results. Rados Bench for benchmarking. Rados Bench allows you to benchmark the performance of the Ceph cluster. It can be used to simulate different workloads and measure the read/write performance. Example, benchmarking write performance *PRBD_pool, specifies the pool to benchmark. *bench 60 write, performs a write benchmark for 60 seconds. *T16, uses 16 threads for the benchmark. *no cleanup, prevents automatic cleanup of the benchmarking objects. Useful for further analysis. Example, benchmarking read performance Grafana and Prometheus integration Grafana and Prometheus are powerful tools for monitoring and visualizing Ceph metrics. Prometheus collects metrics from the Ceph cluster, and Grafana displays the metrics in a user-friendly dashboard. 1. Install Prometheus Exporter *. The Ceph exporter exposes Ceph metrics to Prometheus. There are community-developed exporters available. One popular option is Ceph Exporter. 2. Configure Prometheus *. Configure Prometheus to scrape the Ceph exporter. 3. Import Grafana dashboard *. Import a Grafana dashboard to visualize the Ceph metrics. Many pre-built dashboards are available online. *OSD profiling with perf and flame graphs Perf is a performance analysis tool that can be used to profile the OSD processes. Flame graphs are a visualization tool that can help you identify the functions that are consuming the most CPU time. 1. Install perf *. Install the perf package on your OSD nodes. 2. Record performance data *. Use perf record to record performance data for the OSD process. Replace OSD_PID with the process ID of the OSD. Use Ceph OSD status to get the PID of each OSD. 3. Generate flame graph *. Use the flame graph tool, available on GitHub, to generate a flame graph from the perf.data file. The flame graph will show you which functions are consuming the most CPU time. This can help you identify performance bottlenecks. 6. Advanced RBD features and techniques. *RBD snapshots and cloning snapshots create point-in-time copies of RBD images. Snapshots are read-only and space-efficient. Cloning create new RBD images from snapshots. Clones are copy-on-write, meaning that they only store the differences from the snapshot. Use cases backups. Testing. Virtual machine deployments. RBD mirroring, disaster recovery. RBD mirroring allows you to replicate RBD images between two Ceph clusters. This provides disaster recovery capabilities. In the event of a failure in the primary cluster, you can fail over to the secondary cluster. Steps *. 1. Configure mirroring *. Ensure both clusters can communicate. Create a mirroring pool on the secondary cluster. 2. Enable mirroring on the primary pool *. 3. Add the secondary cluster as a peer *. UUID, the pool's UUID on the secondary cluster, found with Ceph OSD pool get pool_name pool. *client_name, the client name on the secondary cluster, example client.admin. *mon_host_list, a comma-separated list of monitor hosts on the secondary cluster. 4. Enable mirroring on RBD image *. 5. Monitor mirroring status *. RBD encryption RBD encryption allows you to encrypt RBD images at rest. This protects the data from unauthorized access. Ceph integrates with the Linux kernel's dmcrypt framework for encryption. Steps *. 1. Load the dmcrypt module *. Ensure the dm_crypt module is loaded in the kernel. 2. Create an encryption key *. Generate a random encryption key and store it securely, example using HashiCorp Vault or similar secret management. 3. Map the RBD image with encryption *. 4. Format the map device *. Important security considerations *. Key management *. The encryption keys must be stored securely. Do not store them directly on the OSD nodes. Key rotation *. Implement a key rotation policy to periodically change the encryption keys. Quality of service, QoS, using Ceph OSD priority *. You can configure QoS for RBD images by setting the priority of the OSD processes. This allows you to prioritize I/O requests from specific virtual machines or applications. Example *. 1. Identify the OSD PIDs *. Use Ceph OSD status to get the PIDs of the OSD processes. 2. Set OSD priority *. Use the renus command to set the priority of the OSD processes. Lower niceness values indicate higher priority. Warning *. Setting a very high priority for one OSD process can negatively impact the performance of other OSD processes. Use with caution. This is a basic approach. More sophisticated QoS mechanisms might be needed in complex environments. 7. Troubleshooting common RBD issues. *OSD down/out issues *. Symptoms *. Ceph S shows OSDs in a down or out state. Performance degradation. Data unavailability. Troubleshooting steps *. 1. Check OSD logs *. Examine the OSD logs for error messages. The logs are typically located in /var/log/ceph/cephosdstar.log. 2. Verify network connectivity *. Ensure that the OSD can communicate with the monitors and other OSDs. 3. Check disk space *. Ensure that the OSD has sufficient disk space. Use DFH to check disk usage. 4. Check OSD process *. Ensure that the OSD process is running. Use PS auxiliary grep Ceph OSD. If it's crashed, restart the OSD. 5. Examine hardware health *. Check the physical health of the underlying storage hardware. 6. Monitor health alerts *. Pay attention to Ceph's health alerts. Slow request errors, slow operations. Symptoms applications experience slow response times. Ceph S shows slow requests are blocked 32 SEC. Increased latency. Troubleshooting steps *. 1. Check OSD load *. Use IOStat or top to check the load on the OSD nodes. High CPU or disk I/O utilization can indicate a bottleneck. 2. Check network performance *. Use ping or trace route to check network latency between OSDs and clients. 3. Analyze OSD logs *. Examine the OSD logs for error messages or warnings. 4. Check PG states *. Use Ceph PG stat or Ceph PG dump to check for stuck or degraded PGS. 5. Investigate long IOS *. Use the Ceph daemon OSD_ID perf dump_historic_ops to examine the recently completed longest IOS handled by the OSD. Performance bottlenecks *. Common bottlenecks *. Insufficient CPU or memory on OSD nodes. Slow storage devices. Network congestion. Incorrectly configured crush map. Inadequate number of PGS. RBD client misconfiguration, example incorrect cache settings, I/O scheduler. Asterisk troubleshooting steps asterisk. 1. Identify the bottleneck asterisk use performance monitoring tools, example IOStat, TOP, Grafana, Prometheus, to identify the bottleneck. 2. Optimize hardware asterisk upgrade the hardware if necessary. 3. Tune Ceph configuration asterisk adjust the Ceph configuration parameters to optimize performance. Revisit crush map design. 4. Optimize RBD client configuration asterisk adjust the RBD client configuration parameters to optimize performance. Experiment with different cache settings and I/O schedulers. 8. Best practices for Ceph RBD management. Asterisk regular monitoring and alerting asterisk. Asterisk implement a comprehensive monitoring system to track the health and performance of the Ceph cluster. Asterisk set up alerts to notify you of potential issues. Asterisk regularly review the monitoring data to identify trends and potential problems. Asterisk capacity planning asterisk. Asterisk estimate your storage requirements based on your workload. Asterisk monitor your storage usage and plan for future growth. Asterisk consider using tiering to optimize storage costs. Asterisk software and hardware updates asterisk. Asterisk keep the Ceph software up to date with the latest releases. Asterisk apply security patches promptly. Asterisk regularly check the health of your hardware components and replace any failing components. Asterisk follow Ceph best practices for upgrade procedures. Asterisk security hardening asterisk. Asterisk secure the Ceph cluster by implementing appropriate security measures. Asterisk restrict access to the cluster to authorized users only. Asterisk use encryption to protect data at rest and in transit. Asterisk regularly audit the security configuration of the cluster. Conclusion asterisk. This guide has provided a comprehensive overview of advanced tuning and operational aspects of Ceph block storage, RBD. By understanding the concepts and techniques presented in this guide, you can effectively manage your Ceph RBD clusters and optimize them for performance, reliability, and scalability. Remember to test any configuration changes in a non-production environment before applying them to a production system. Continual monitoring, analysis, and adaptation are crucial for maintaining a healthy and efficient Ceph RBD cluster.